You watch a developer type a quick prompt into an AI assistant, and seconds later, a complete authentication module appears on their screen. While that code populates, two things are happening in the background. Proprietary source code is being routed to external, third-party servers to process the request, and the AI is actively inventing logic based on its global pre-training, totally divorced from your internal security standards. If an error or a breach stems from that code, standard logging systems will not save you. A system administrator with root access can simply clear the database records, erasing any trace of the AI prompt or the data exfiltration. Enterprise architects frequently rely on prompt engineering to constrain the AI, and standard database logs to track the operators. This assumes the AI will obey instructions and the operator will act honestly. In high-security, defense, or public sector environments, relying on a human to verify the output or guard the log file is a structural vulnerability. Human oversight is easily bypassed or manipulated. To secure an AI development environment, you have to physically and mathematically eliminate these vulnerabilities from the ground up. You must deploy a zero-trust on-premises architecture. Enterprise AI security requires impassable architectural constraints. We cannot ask the system to be safe. We have to engineer it so that it has no other option. The first principle of control is restricting the model's context window. An open-ended language model uses its pre-trained global knowledge to fill in the blanks. When a model guesses using outside data, it generates code and architectural recommendations that conflict with your specific internal design decisions, APIs, and security policies. To eliminate this, we isolate the AI inside a project knowledge graph. When a user submits a query, the system bypasses global knowledge and searches only these verified internal nodes to build the context. If the system fails to find a matching internal node, it executes a hard rejection protocol. The connection to the LLM is severed before a single word is generated. When an answer is generated, the system enforces a mandatory citation rule. Every line of code or technical claim must explicitly tag the exact internal file, database schema, or policy document it referenced. Because this entire process runs on isolated local inference engines, like VLLM or llama.cpp, your proprietary data never touches the public internet. We eradicate hallucinations by systematically starving the AI of the ability to fabricate, forcing it to act strictly as a synthesizer of verified internal facts. A written security document is passive. It only works if developers choose to read and follow it. This diagram shows how we convert policies into executable gates. The central LLM is permanently flanked by pre-response and post-response firewalls. The pre-response guard evaluates every incoming prompt, validating authorization and security tier before the query reaches the model. The post-response guard intercepts the generated output. It scans the text to block unverified claims, missing citations, or raw credentials. This dual-gate architecture neutralizes prompt injection and jailbreak attempts at the system layer. We secure the environment without having to constantly retrain or modify the core model's underlying weights. If an admin attempts to bypass a baseline policy, the system requires multi-party approval and generates an immediate audit event. Policies dictate behavior only when they are engineered as unavoidable choke points in the data pipeline. Constraining the AI is only half the architecture. We also have to track the developers and administrators interacting with it. Traditional database logs are editable. Anyone with root access can alter a timestamp, delete an AI query, or erase a deployment record without leaving a trace. The history belongs to whoever holds the highest permissions. To achieve true independent auditing, we use an append-only hash chain. The cryptographic hash of one row permanently locks into the payload of the next. Every AI prompt, generated response, code commit, and policy adjustment is permanently sealed into this sequence. If an operator attempts to alter a single character in a past event, the mathematical link is broken, and every subsequent hash down the chain instantly turns red. The system hashes its own baseline policy manifest at server boot. Unauthorized configuration drift is immediately detected before a single line of code is written. For high-security tiers, these chains are replicated to write once, read many, and secured using Merkle tree root sealing to ensure total data permanence. Trust requires mathematical proof. We designed the audit layer so that covering up a breach or a mistake is impossible. A perfect audit log still fails if an attacker operates through a legitimately provisioned, compromised developer account. Recording who performed an action provides an incomplete picture. The system must also prove exactly where that action originated. Every single system request undergoes dual identity verification. The architecture demands both a verified user token and a cryptographic certificate from a registered physical machine. If valid user credentials are used on an unregistered terminal, the system forcefully rejects the connection. Once identity and origin are verified, those identities are mapped to a strict separation of duties. The boundaries are absolute. Operators can deploy infrastructure, but cannot modify audit logs. Developers can query the AI, but cannot alter security policies. To verify all of this, external auditors are given a completely isolated, read-only portal. They can trace hashes, view compliance maps, and log their findings without any operational access to the core system. An audit trail is only valid when the power to commit an action and the power to erase it belong to completely different entities. Let's look at that same developer requesting a new authentication module, but this time the request is executed within the secured framework. This diagram illustrates the complete zero-trust architecture. A query clears the dual identity check, strikes the pre-response gate, routes into the localized knowledge graph, processes inside the isolated LLM, clears the post-response scanner, and finally stamps into the database. The final generated code arrives carrying its own proof: strict internal source citations, explicit impact parameters, and a permanent cryptographic receipt linking it to the exact model, policy, and user terminal. This pipeline subjects every interaction to the same rigorous oversight as human-written code. By treating the model as a utility within the enterprise control plane, we ensure all AI generation is auditable and contained within existing security bounds. Because every control is built directly into the system layer, this architecture intrinsically satisfies stringent frameworks like ISO 27001 and NIST Zero Trust, automatically generating the proof required by regulators. Deploying enterprise AI is not a matter of installing a smarter model. It requires engineering a resilient environment where security and auditability are hard-coded into the entire data flow itself.